let's continue our discussion of Fourier transforms. We'll continue discussion of some common Fourier transforms, and let's first look at Fourier transform of periodic signals. From our work with Fourier series, we know that any periodic signal can be written as the following sum, minus infinity to infinity of d of n e to the j n omega 0 t. So this is just the exponential Fourier series. And then we found previously that this complex exponential has a Fourier transform of 2 pi delta omega minus the frequency of this is n omega 0. So each one of these exponentials will transform as an impulse located at well, when n is equal to 0, it'll be located at omega equal to 0, but then when n is equal to 1, it'll be located at omega 0, 2 omega 0, 3 omega 0, and so on and so forth. So putting the two pieces together, the Fourier transform of x of t then is just the Fourier transform of each of the terms in the sum. I'll pull the 2 pi out of the sum. The dn's are of course just coefficients, and then each of the impulses transforms as an impulse like this. So a sketch of the corresponding spectrum x of omega when n is equal to 0, we'd have an impulse at omega equal to 0, and the weight of that impulse is 2 pi d0. Then there is also going to be another impulse at omega 0. The height of that will be 2 pi d1, and then at minus omega 0 with weight 2 pi d of minus 1. Know that d of minus 1 and d of 1 are a complex conjugate pair when x of t is a real signal, so these would have the same height. And then also at omega 2, the height or weight of these actually depends on the Fourier series coefficients. So again, this would be the same height as the, actually these are 2 omega 0, 2 omega 0 minus 2 omega 0, and 2 pi d of minus 2, and then these would just continue on. There's one special case that will arise when we look at sampling. That's an impulse train, or sometimes called a comb, and that is it's an ideal signal that in the time domain just consists of a bunch of impulses. I'll let their spacing be t0, so it's an infinite train of impulses in both directions. Okay, so this is called a comb or an impulse train. The weight of each of these impulses is 1. And again, this will first arise when we talk about ideal sampling, which is related to practical sampling of signals. We can represent this comb as an infinite sum of shifted impulses from minus infinity to infinity of just now. These are all in the time domain, just all located at multiples of n times the period. Sometimes you'll see this represented as using this notation. It's a subscript here. The subscript tells you that it's an impulse train with a period of t0. So sometimes you'll see this alternate notation used to represent the comb function. So this is a periodic signal, so it does have a Fourier series representation. And if you work through the calculation of the Fourier series coefficients, you'll see that all of the Fourier series coefficients are equal to 1 over t0, jn omega 0 t. So all of the dn they don't depend on t0 for this special case. They don't depend on n for this special case. They're all equal to 1 over t0 for all n. And then based on the work on the previous slide, x of omega then would be 2 pi. I'll pull out the 1 over t0 term, and then we have a sum from minus infinity to infinity of just omega minus n omega 0. So this is the same sum of impulses that we had for a periodic signal previously, which of course this is a periodic signal, but now all of the weights of all of the impulses in the frequency domain are equal. So corresponding spectrum would look like this. It has a weight of 2 pi over t0 at 0, and then we have component at omega 0, 2 omega 0, minus omega 0, minus 2 omega 0, and these continue on forever, and all of these impulses have the same amplitude. So an impulse train in time actually has a Fourier transform that is an impulse train in frequency. Let's look at 2 other common transforms. Unit step arises a lot. We've seen that. So x of t is equal to u of t. The transform in this case, I'll state without proof, is pi times delta omega, so it consists of an impulse at the origin plus 1 over j omega. So if I were to try and sketch, of course this is a complex function, so I'd have to sketch the magnitude and phase. It does have an impulse here at the origin at omega equal to 0, and then the magnitude spectrum, we're going to add into that a 1 over omega function, so that would look like this, absolute value of 1 over omega. So this is the magnitude spectrum, would have this shape. Phase angle is going to be equal to plus 90 due to this term, actually minus 90 for positive omega, and plus 90 for negative omega due to that term. Related to the unit step is another function often called the signum function or the sine function. And the notation we use for that is x of t is equal to signum of t. It's an extremely simple function. It's equal to 1 for all positive t, just like the unit step, but instead of being equal to 0 for negative t, it's actually equal to minus 1. So this is the signum function. Actually, it's related to the unit step. If you multiply the unit step by 2 and then subtract 1, you'll get the signum function. So there's this relationship between the two. And Fourier transform of the signum function is actually just 2 over j omega. So that magnitude spectrum will look like this. 1 over omega shape. One easy value to find is at omega equal 2, where the magnitude would be 1, and similarly at minus 2, it's also going to have a height of 1. Another way to write this is I'm going to multiply numerator and denominator by j. I'll get a minus 1 in the denominator. And so I can rewrite like this, which makes it easy to see that as long as omega is positive, the angle of this will lie on the, for positive omega, this point will lie on the negative imaginary axis. For negative omega, this will be on the positive axis. So for all positive omega, saying this will have a phase angle of negative 90 degrees, and then for all negative omega, it will have a phase angle of plus 90. So this is the phase spectrum of the signum function. Table 7.1 lists several other transforms. I will provide a handout in class that's just a little more convenient to use when you're working through the homework problems.